In previous videos, we built our system design comprised of line arrays, subwoofers, and point sources. In this video, we will explore the various model and data views available in system activity that you can use to calibrate your cohesion system design and gain crucial insights into system performance before the system is deployed. In the system mapping and simulation video, we talked about how system simulation within Canvas is designed to behave like a real-world PA system. In Canvas, the calibration workflow we use is also identical to how we would calibrate the system on site. We'll begin by examining the main line array system in the design. Because we are interested in a single array's cross-section, we should verify that only one side of the stereo pair is unmuted. We can easily configure this by soloing the array pair and then muting one of the two sides. In this case, I will mute the left side of the PA. Now, we set up Canvas to display two panes, viewing the array's cross-section and SPL over distance data views. Next, let's make sure that we have dot mapping active and ensure the SPL map is visible. In the cross-section view, Canvas displays a 2D view of the array and the corresponding venue geometry, which intersects with the on-axis aiming of that array. Vertical aiming can be simply adjusted in cross-section by left-clicking and dragging the top enclosure's aiming line. In this model, we'll likely be looking for a little overshoot. Aiming lines are projected from each enclosure of the array, and when an aiming line intersects a seating section, a dot is added at that point which displays the current SPL value, based on the simulation settings. Hovering over the dots in cross-section displays the SPL values. SPL dots in cross-section behave identical to that of the 3D view. Keep in mind, any enclosure array that does not intersect an audience plane will not be displayed. In the SPL over distance view, we're looking at the on-axis SPL dataset, continuously sampled for all seating sections that are on axis to the selected array. Each line in the graph is color-coded to match the color of the seating section in the venue model, making it easier to interpret the data. Notice the cross-section and SPL over distance views share a locked x-axis. When you manipulate one, the other tracks with it. Remember, all SPL data in these views are based upon the current mapping calculation settings. Any change in the spectrum frequency or bandwidth settings will be reflected in the SPL data. Generally, cohesion systems are designed to achieve a 2 dB roll-off per 100 feet when using a 3-octave bandwidth, centered at 2 kHz for the calculation setting. We'll update a few parameters on the array to meet this criteria. Once updated, we should also review the low-mid response of the array. In an effort to achieve minimal spectral variance across the vertical geometry, we'd be looking for a similar roll-off as before, but this time using the 250 Hz 1-octave setting. To evaluate spectral variance of the selected array, we can use the magnitude over distance data view in a third pane. By selecting enclosure from the resolution drop-down option, we are now viewing the magnitude response at each impact point shown in the cross-section data view. The amount of data points can be changed by selecting low, medium, or high within the resolution drop-down. These data points correspond to the cross-section view and are represented by small dots within each seating section. Notice as we increase resolution that more dots appear. Hovering over any of the data points will highlight the corresponding magnitude trace between views to help with correlating the data between the different views. Canvas includes additional tools to look at spectral variance across multiple sources. Using the measurement line tool, we can look at the magnitude responses of multiple points over the distance of a defined centerline vector that intersects with front of house. We can apply a measurement line in the top view by clicking on the measurement line tool in the toolbar. You can place the start and end points directly on the y-axis and move the x-axis to cover a large majority of the venue. Now we are interested in the overall summation between the left and right array pair, so we are going to unmute the left side of the PA while still keeping the pair soloed. And now you are seeing a set of magnitude responses equally spaced along the measurement line according to the resolution I have specified. The measurement line comes with a few extra options to normalize the data. This is a great tool to quickly check spectral deviation from the middle point of the line, an average of all points along the line, or even a user-defined measurement point, like a front-of-house reference. Now, let's add a measurement point for the front of house location. When thinking about where to place measurement points in your model, consider adding them in Canvas in the same locations that you would place a measurement mic when collecting data to verify performance on site. One tip on measurement points: they utilize the snap settings that are employed by other elements within the venue model. You will notice that when moving the measurement point, it will automatically snap to a surface in the Z-axis. The snap distance used is defined in the application settings. Now that we have the front of house reference mic, we can look back at the center measurement line and look at spectral deviation from the front of house mix position. To evaluate the reference position further, we can use our newly created measurement point and look at system response. To do this, I can use the magnitude response data view. Again, not only do open sources contribute to the data you are viewing, but also any physical or DSP settings of the individual sources. Placing multiple measurement points in the simulation will overlay the individual magnitude data on the same graph, making correlation and variation assessment simpler. Once satisfied with the main line array configuration and its contribution to the front of house reference position, we'll begin evaluating the other sources in the design and aligning them. We will begin by looking at the alignment between the main hangs, the flown sub, and the ground subsystems. To look at the infraband overlap and interaction, we will switch the second pane to the phase data view. In this view, we'll analyze the phase shift across frequency at the measurement point selected. In this design, we might want to align the subsystems on axis of the main arrays at the on-axis mains front of house reference point. Using the on-axis mains front of house measurement point as my measurement location, you can define a reference phase trace. In this particular deployment, your flown subarray will be times 0, and the main arrays and ground subarrays will be aligned to the flown sub. Select the flown subs here for reference, and because we are looking at the left side, it'll be the M suffix. The white line is the reference channel to which we want to align the live colored trace. Now, in the source list, we want to select our main hang source pair and ensure that the main left is the only active source. Within the processing tab, we can start applying delay, looking to align the phase response at the crossover frequency and below as closely as possible. Next, we'll look at the ground subarray from that same measurement location. We will begin by soloing the ground subarray and muting the right side. Delay should be applied across the ground subarrays until the color trace closely overlays on the white reference line. Verifying the alignment can be done by evaluating summation one source group at a time. Opening a third pane and evaluating summation at the on-axis location or stereo summation at the front of house reference position are quick ways to verify. And of course, the same process can be then applied for additional full bandwidth source alignment like the side system in this project. One of the nice time savers in Canvas is that because of the pairing feature, you only need to work on one side of the PA, and all of your settings are simultaneously applied to the mirror paired source. When working with a distributed fill deployment, we typically recommend an impulse response alignment. Now I will change my phase response data view to a time arrival data view, which is a simplified impulse response view of the system that shows only the direct arrival at the selected measurement location for all active clusters. In this data view, the x-axis is the time domain and the y-axis is the level of each discrete arrival at this measurement location. Unlike the real world, microphones are cheap in Canvas, so we'll be adding another measurement point for front fill alignment in this design. I will place the microphone on axis of the most on-stage front fill just within the coverage of the bottom of the main arrays to evaluate the propagation time difference. Currently, we only have the left main array unmuted, indicated by this arrival pin. Hovering over the arrival pin displays data for this arrival at this particular measurement location. When we unmute the inside front fill, we can see its arrival on the same graph. Now, we have a few options. You can simply subtract the time difference between the two to achieve IR alignment. Or, you can let Canvas do the work for you by selecting a relative data view. To do this, select the main array option under Relative to Source in the Data Type dropdown. Now, when we hover over the front fill time arrival pin, we are given the delay offset relative to the mains. Inputting that delay into the processing field updates the simulation, and you can see that the front fill is now perfectly aligned to the main array, and hovering over the bars results in 2 data readouts with 0 time offset. Now we just need to repeat this process for each of our front fill pairs. One more note, remember that studio views can be saved and recalled using the Studio View tool in the bottom left of the Design Studio. Create, store, and recall the views that work best for your calibration workflow using the Studio View tool in the bottom left of the studio. This concludes the calibration workflow overview. In this session, we covered a lot of material, including evaluating the performance of an array using a number of data views, using the phase response to align mains and subs, and using the time arrival data view to perform alignment of our front fills to our main PA. You have now completed the Canvas Quickstart series. Thanks for watching.